Before the workshop starts, we're going to show you how to navigate through the video. Below the YouTube video is the Show More button. Click the Show More button to reveal the index. You can skip to the point that you want in the video by clicking the blue time link.
Program for today. With the morning we're looking at problem solving, and then in the afternoon we have teaching and learning plans. Right, it's better to travel than to arrive is what we're saying in the workshop. I suppose I've been travelling for 37 years now on the whole maths education, and I'm learning the whole time, and it's been, most of the time, it's been a brilliant experience, and particularly these last couple of years working with Project Maths. It's given me, anyway, a new lease of life. We're going to start the day with a little quiz. So a set of 6 questions, and if you have a minute, I have a countdown timer. If you have a minute, just jot down A, B, C and D are the answers. Okay? So if we start. Which of the following celebrities did not study pure mathematics in university? So let's see who it is. It's actually Carl Vorderman. And though a lot of people think she studied maths, she studied engineering. Okay? Next one. A regular octagon has an internal angle of how many degrees? Right. It's 135 degrees. Okay, next one. A perfect number is a number whose factors, excluding itself, add up to the number itself. I'll give you an example there of 6. Which of the following is a perfect number? It's 28. We take all the factors of 28 and add them up, it comes to 28. Next one, who said, it's not that I'm so smart, it's just that I stay with problems longer. So we have Albert Einstein. The sum of the 3 most beautiful and intriguing mathematical constants, pi, e and phi, is closest to which integer? And we have 7. All right, well, we should have got that right. Pi 3.14, e 2.718, and phi 1.618, sum to 7.459. So nearest to 7. And which of the following have won a Nobel Prize for mathematics? Okay, and the answer is none of these. There isn't a Nobel Prize for maths. Now, this next slide is a time frame of where we are with Project Maths and where we're going with it. Okay. Project Maths started in, we leave the pilot aside, the pilot schools, we're talking about the national rollout. Project Maths started in September 2010 for what we call the national rollout. And it started with first years doing Strand 1 and 2, and 5th years doing Strand 1 and 2. Strand 1 being statistics and probability, and Strand 2 being geometry and trigonometry. And that means that, if we look at these first, these current, they were last year's 5th year, they're the current 6th years. They're facing a partially changed exam this June. And I'll talk about that in more detail later. And the same with the junior certs, the 2nd years there now, they're facing a new exam in 2013. It's paper 2. Both strands 1 and 2 are paper 2 material. So for higher level leaving certs, all of paper 2 is completely changed. Ordinary level and foundation level leaving certs, they still have the traditional area and volume question on the paper. So I said I explained that in more detail when I have a slide on it towards the end of the day when we're talking about assessment. Then last September, the incoming first years, as well as doing strands 1 and 2, are doing strands 3 and 4. 3 is numbers, and 4 is algebra. And the same with the current fifth years. So these are your current first years, and these are the current fifth years. And that means there's only 5 strands in the syllabus. So it means that when they go to do their exams, junior cert or leaving cert, they will have pretty much full paper change. All of paper 2 is changed and most of paper 1. The only thing that's not changed are functions for the junior cycle students and functions in calculus for the leaving certs. So it'll be next year before the first group of students come in to our first year group who start and will carry project maths the whole way through. The students in 5th and 6th year haven't done any project maths at junior cycle, so there's a bit of backfilling required, and for that purpose, because of that, there have been some material has been deferred in the interim. But when this group of first years make their way right up to 5th year, like the whole syllabus will be in at that stage. So any questions on the actual rollout of the syllabus? So you're not involved on the ground sometimes, people are not particularly aware of what's happening. Obviously the students are the most important aspect in all of this. So it's a way to learn new maths. Sometimes setting them a problem, it'll get their enthusiasm going for how, even if they have the skills, it's great, they can use it. But if they haven't the skills, it gives them the enthusiasm to hopefully acquire the skills. And then, as I said, if they have the skills, it's a way to practice what they know already. It's an insight into the work of mathematicians. I think that's an interesting one, because I know my students anyway, they think they can give you any maths problem and you can work it out. And as teachers, we arrive into our class prepared and we have the answers already worked out. So the students have the idea that we can do all of this. So if they can kind of work with problems and have to tease it out in that there isn't always, one correct way of doing the question, and there isn't always an obvious path to the question. And I know over my years of teaching, I don't know whether it's brave or foolish, I've been told I've been both to do it, but I've sometimes gone into students with the questions that I haven't prepared myself and let them talk them through what my thought processes are. Builds confidence, obviously, if they're getting them right. So we have to be very careful. I think it's coming up in a later slide that we differentiate between the types of problems we give the students, that they should be able for them. And obviously, if they're building confidence with them, it'll produce positive attitudes to maths, which, let's face it, isn't out there. A lot of students, a lot of society in general, think it's okay to say, I'm no good at maths, and boast about it as well. Whereas, when you're at nobody says, I can't read. Well, sorry, they keep it very, 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 very private. It's not something they boast about. So we hopefully have positive attitudes to maths. Encourage cooperative skills. We talked about group work here. And make it all enjoyable. It's on the syllabus. I suppose if you can't convince your students for no good reason, it's on the syllabus. And this sort of thing of applying their knowledge to unfamiliar as well as familiar circumstances or questions, contexts. This has always been in the old, let's call it the old syllabus, but it's been in the aims and the objectives. And let's face it, not many people read those, and if they do read them, they read them once. Where it's the main body of the syllabus that people go over to check that they have covered the various aspects. This paragraph, or one very similar to it, is at the end of each of the 5 strands. And it's there in the body of the syllabus. So if you like, it's rebalancing what was there already. Problem solving, I suppose, lip service was paid to it in the old syllabus. Questions that were considered to be problem solving eventually became routine. And we'll be looking at some of those in a few minutes. So we're rebalancing the syllabus. We're going to have procedural type questions and problem solving questions. But hopefully there is a balance between them. From the few exams we've seen so far with the project schools, the balance has been redressed. So it's on the syllabus, so students have to engage with problem solving. It's an economic imperative that we have problem solvers. Let's face it, we need them badly. We need them quickly as well. So we want to create an adaptive, flexible and creative workforce. And finally, life skill. And we mentioned this already here, and they're just various problems people have. I like this one, Christmas, trying to untangle your Christmas tree lights. fact, we haven't roads like that yet in Ireland, but we've got around building your own house, looking for your luggage and left luggage, surgery, and I suppose it's generally life in general. We need to problem solve all the time. So we just looked at there really is why problem solving is important. Now, you all should have a white booklet in front of you, have you? On these next couple of pages, pages 1 to 4, we've questions from, some of them are from Junior Cert and some of them are from Leaving Cert. And what I'd like you to do is, you see the box in the top up here, procedural or problem solving. I'd like you to tick one box. Do you consider this question to be procedural or problem solving? And maybe you can't make up your mind over some of them, you might just put a star beside it. So I want you to put one tick in each box, and even different sections of a question have been broken up, because the A part might be procedural, but the B part might be problem solving. We asked a group of maths teachers, and I've one prepared already if you like for you. This is a slide, and this is only one particular group of teachers, what they thought the questions, whether they were procedural or problem solving, and I'm not suggesting that they're correct or not. But I suppose what I'd like to look at is this one here in particular. Like, look at the divergence of opinion on that. Like, where some of them, they're very much to say, like, the large majority say they're procedural, or large majority say they're problem solving. That one there, that's the last one. So let's have a look at this one in a bit more detail. Okay. Now, let's break it down bit by bit. Would you think the first part of that is procedural or problem solving? The first time students see this, it's a problem for them. But tried and tested, I mean, this type of question has come up year in, year out on the Junior Cert higher level. So after maybe the first couple you do it, the students know, they know the procedure for doing it. The students need to know how they have to put the first two answers together. And I think there's €100 of a difference, isn't there? Yeah, €100. So they know they have to set up some sort of an equation. But you know what? A bit of hit and miss, they might get it right and they mightn't. And they mightn't even be thinking about it. They just know that I put the first one and the second one together, and I put the 100 on one side or the other. And, okay, it's problem solving, yes, to get it fully right and understand it. But you can get it fully right on a hit and miss basis as well. So we'll have a difference of opinion there. And how about the last part? That's very procedural. I mean, they may have ended up with an equation that's not, they can't solve it, but they can go through it. Now, students have, believe it or not, have done well in this type of question. It's usually been marked as 4 5s. And the majority of them get the first 5, the majority get the second 5. It's a bit of hit and miss whether they get the next, but there's an attempt mark. So they get 2 marks, attempt mark, and if they get it wrong, as long as they have some sort of an equation set up with the 2 answers from the first part and the 100 in somewhere, they're getting 2 marks. And then if it's completely, can't possibly solve what they end up with, but they make some attempt at solving it, they get another 2 mark. So this question has ended up being, it's a C part of a question, which was originally conceived as being the hard part, the problem solving part. But over the years, it has become very procedural. And students have been getting around 14 out of the 20 marks for it. And they don't understand. Well, sorry, that's probably exaggerated. But a lot of them would not understand what they're doing. But this type of question started back around 2005. It became this sort of procedural question. Pre-2005, the question would have been written something like this. Now, it's the exact same question. But would you agree with me that that is a problem-solving type of question? But more so anyway, at least, more so than the previous one. And as well as that too, they put the question in context. I mean, even the other one was poor enough in that it just asks you, if you can read it, see it there, solve this equation to find x. It didn't even say solve this equation to find x and therefore find the number of people who shared the prize. It didn't even put it in context. So that was the type of question that was on the higher level Junior Cert up to about 2005, and from then on they changed it for whatever reason, don't know. But obviously it made it much easier. And it became very procedural. Until one year, they threw in one that looked like it was the very same. It's not in your list there. We refer to it as the bale of hay. And it's a farmer feeds bales of hay. But if you read through the question, you can see it's just a little bit. I mean, on my reading as a teacher first, I didn't see the difference until the students came out and they did not. I'm not talking about just my students, I'm talking about students all over the country. It was a bit different to what had gone on in previous years, and there was uproar on it. And there were people on the papers and all the questions about it. It wasn't the same as the previous ones. Okay? So this has been part of the problem, has been the predictability. In the previous one, just to see what the difference, you had the 2,000 divided by x and you had your 2,000 divided by x plus 1. And when you came on to this one here, you have your 540 divided by x, but it's not the same number. That's all the difference was. It wasn't the same number for the second part divided by x plus 1. It was, 300 divided by x plus 1. And setting up the equation and all that, so it was very poorly answered. Okay, so let's look at this one then. Can you see how different this is to previous exams questions? Even just looking at the exam questions that are the sample we've given you. But if you've been more experienced of Leave Insert at higher level or ordinary level, doesn't matter which, that question was a lot different from it. What's the main differences can you spot in that question? Words. It's heavily laden with words. And I can say to you that is, if it's any single one gripe I'm getting out on the road with the workshops, is how much language is involved in the questions. Picture caused a bit of controversy too, and like this railing around it was not quite as obvious what they meant by it. Do you notice the lack of numbers in it? The only number we have really of any significance is the 10 degrees here. I mean, measuring tape being 100 metres doesn't really matter. I mean, if you want to measure it, you can measure 200 or 150 or anything like that. Did cause quite a bit of upset amongst teachers and students. And I'll just show you the next slide, a report from the actual report on it. This question was not well answered. It appeared that candidates had little experience of applying their mathematical knowledge in this way. The trigonometry involved was not difficult. In fact, it was very easy. It was much easier than anything that would have come up at a higher level Leave Insert paper traditionally. And one would expect it to be well within the compass of moderately good candidates. However, at this stage, the candidates clearly had little experience of planning and undertaking field activities, or of discussing the practicalities of using trigonometry to solve real-life problems. And part A required verbal answers. I mentioned this to you earlier on. Like, so you've got to justify your answers or explain your answers, so there's a lot of verbal answers rather than mathematical work. As with other such questions on the paper, for most candidates this proved difficult. So we've got to try and change what's happening in our classrooms, that students are discussing the maths. They're not just sitting down, writing it down and calling out an answer. That they're discussing what they're doing, and the problem solving, of course, allows them to do that. But they need to be able to discuss their answers, they need to be able to justify their answers. Now, on page 4, I saw some of you filling it in when you finished the questions. We ask you to list 3 characteristics of questions that are problem solving questions. I know a few of you have it done, but if the rest of you could mind doing it now, please. Alternative approaches, yeah. There isn't always just one way of doing it. Okay, you've got to consider all the options. Anything else? Okay, must connect to prior knowledge. Deduce what procedure to use. Okay. Unfamiliar. So something they haven't seen before, but we don't want our students to be frightened of them if we've sufficiently prepared them that they know, okay, I've never seen this before. But if they put it on the exam, it is something that I should have the means to solve it from what I've learned in class, so that they're not frightened by it. So unfamiliar frightens the wits out of the teachers, and it's frightening the students at this stage. But if we work through it, hopefully it's something that they will actually look forward to doing. Okay, so extract the maths information from the general information. We see a lot of these problem-solving questions have a lot of words in them. So I don't mind if I add that one to myself, which is D-Y, wordy. Wordy questions, which is basically what leads them then to needing to be able to extract what actually is necessary. Traditionally, in a lot of questions, you'd find that they never gave you superfluous information. You had to use every figure that was given to you. You send the students along underlining all the numbers on the questions. These are kind of the techniques you tell them. And you're going to have to use every one of those. But they can be distracting pieces of information in among a problem-solving question. And that one there with the pylon, it didn't matter that the measuring tape was 100 metres, but students were fixed in that they had to use it. We're trying to change the classroom from the traditional classroom, which I would have loved, with everybody staying perfectly quiet, heads down, do the question, get the answer right, move on to the next one. Plenty of practice at it. What we need to, and this is a challenge for us all as teachers, is to have a different classroom situation. Instead of sitting in nice neat rows, we might put them in around tables and working together, and particularly in problem-solving questions, and get them to talk maths. And when we say talk maths, we don't just mean talk through how you got the answer you've got, and I added 5 to this side, or I multiplied by 3, but why you did it. Not just what you did, but why you did it. And we're finding that in the reports we're getting from the State Exams Commission, it's getting better, but that has been a big problem for the students. Here is one definition of problem solving. It's solving non-routine problems using skills that you have. When we're saying this, we've already said this, it's connected to prior knowledge. Or gain, because you might have to actually go and acquire a new skill, and it often gives the students a problem if they can't solve it. They haven't the skills to do it, it gives them the motivation to learn whatever skill is necessary. So when finding a solution to a problem which initially seemed unsolvable. Often when you read the question, it doesn't seem like you can see your way through it clearly. So when you read a question and you can't initially see your way to the end of the problem, just take the first step. Draw a diagram, write out what you know, what you've been given, and trust that the answer will reveal itself to you. And we have a picture of driving at night time. When we set out in our car at night time, we can't see, well, even during the day we can't see our destination, but night time particularly, you can just see whatever, 50 metres ahead of you or whatever else. You can't see around the next bend. But you trust when you set out on your journey that you're going to get to your destination. So that's what we're actually saying here. So what we're saying is that these are the way the approaches we could use, or the strategies we could use in problem solving. What we used to call trial and error, it's more PC seemingly to call it trial and improvement. Draw a diagram, look for a pattern, act it out, draw a table, simplify the problem. Use an equation, work backwards, and eliminate the possibilities. And there's probably more. They're the ones we've identified. I'm going to give you a question. Sorry, just go back to that a second. I'm going to give you a question to do. And George Polya says, to be a successful problem solver, don't rush in before you know what's been asked. And he suggests that you make sure you understand the question first. If you want clarification from me, be sure you ask me, please. Make a plan. We're going to try this way. Carry out your plan. Obvious, but maybe not. Carry out the plan. And then, obviously, if the plan works, great. But if that route doesn't give you the answer, you've got to go away and revisit your plan and maybe modify it or take a totally different route. So this is the question. Okay, what is the solution at the end? Which lockers are open when you've the 100 done? The squares. So we discovered either by drawing out tables, as I said most of you did, or with the bricks, as they call them, the unifix cubes. We came after maybe doing 10 that we had 1, 4, 9 open. And sometimes people didn't spot a pattern at that stage until maybe they did another few and discovered that the next one was 16. And then began to wonder, was the next one going to be 25? Okay. So finding the pattern was the big thing on it. And keeping a table, I'll show you a table on two tables on the slides in a minute, but keeping your table accurate it can be difficult, O's and C's, and trying to write things down in different symbols. But that's I think that was the main way in the end that the majority of you got it out. Why, however, the question is then, why? Why are the perfect squares open and all the others closed? And it came down to what? Factors. Okay, factors. So, what do we know about the factors of, what did you discover about the factors of perfect squares as distinct from the factors of other numbers that are not perfect squares? Odd number of factors and even number of factors. So let's have a look at 16, for example. The factors of 16 are 1, 2, 4, 8, and 16. And if we take, say, 18 very close to it, 1, 2, 3, 6, help me out here, 9, and 1, 2, 3, 4, 5, and 18. Am I right there? Now, that's only one set. But we need to be able to project this for the 100 lockers, or in fact the 1,000 lockers. Why is there an odd number of factors with the perfect squares and an even number of factors with everything else? Factors occur in pairs. If we want to make sure that when you're writing out a big long list of factors and you want to make sure you have them all, I would always start with, like for 18, 1 by 18, 2 by 9, and 3 by 6. Okay, whereas you go to the pairs with the perfect squares, you have 1 by 16, 2 by 8, and 4 by 4, but we only write it down once. And that works with every perfect square. Every perfect square, we have a pair of factors in the middle are the same one. So you'll always have an odd number of factors with perfect squares, which will always leave a locker open. And the even number of factors will close the locker. So before we go on to look at some tables, I suppose we look back at our methodologies we were using. Where's the draw table? Draw a table. I suppose that's the one that most of you employed at the end. We did have trial and improvement down here. And I would call working with the manipulative, the unifix cubes, probably acting it out to some extent. Okay? Simplify the problem, which is what most of you did. I mean, you didn't start all, you might have started off with 100 lockers originally, but you said, oh God, this is too long and too tedious, and you simplified it down maybe to 10 or 20 lockers. I suppose your diagrams or your tables. You looked for a pattern. I'd say, when you think of it, we hit an awful lot of these strategies in doing that question. Now, what this here is just a little applet, but we can, sorry, no, a second, I don't even have to physically open them myself, I just can, next student to go. So the first student, if we just look at it, the whole lot of them are open. And if we keep doing that, we can see every second one close, open, close, and so on. Now we're on to student 25. So if you look at the first 25 now, 1, 4, 9, 16, 25. It's just a simulation of it. Okay. I have found myself in doing this that trying to keep my table neat was the biggest difficulty for me, and I came up myself then with the table looking something like that. Once I kind of, after doing the messy one, once I realised that once the first locker has been visited by the first person, it was never touched again. So I didn't actually go back in and fill in here anymore. And I decided then, I think I saw some of you doing that as well, that you just put in what if it remained open, you didn't put anything in the column. But they're just variations on the column. So the extension questions. Which students touched both locker 36 and 48? Or they're just, in general, they're just the common factors of 36 and 48. So once you've cracked it, I suppose that's I think I called it a few minutes ago, the eureka moment. Once you've cracked it, the rest of the extension questions follow on fairly quickly. Which lockers were touched by only 2 students? The prime numbers, right? And the prime numbers, again, we're back to factors. The prime numbers, because they only have 2 factors, and obviously 1 is not considered a prime number, we're including it it was touched only once, I beg your pardon. 2, 3, 5 and so on. Prime numbers, only 2 factors. Which lockers were touched by only 3 students? Now you have the idea, we're obviously looking for the numbers that have 3 factors. So what numbers have 3 factors? The prime numbers squared. If you think about it, any prime number when you square it, so if we take 2 and square it, we've got 4, then its factors are 1, itself, and its square root. Okay, so prime squared, 3 factors, they have 1, they have the number itself, and they have the square root of the number. And the last question is really for the student who has finished it all in advance, and you get them to slog away through all the numbers to find out which of them have the highest number of factors. Isn't that what we're looking for? Which lockers were switched the most time? The most time means how many people, the highest number of people who visited them, and in fact there are quite a number of them. All of those have 12 factors. Okay, the implications for the classroom. We've already had here, it can be a good group activity, although I know you had expressed to me your reservations about starting it as a group activity. Is that what you said? Yeah. With teachers as well, as teachers we have to be very, very careful. If we are doing group activity, that one person doesn't do the problem and everybody else sitting back. And we've got to be very, very careful of that your group, you structure your groups in such a way that you know your own students, that you kind of get them working away at it and that they won't have one dominant person and one person sitting back. But there's a certain, as you said though, there's a certain security as well that you're not, there's a couple of you working on the problem. So group work is the first thing I have up here. Problem solving sessions need to be structured, and I've just said that, by the teacher. And this takes time. I mean, I went through several workshops, or not several workshops, several in-services, and say, group work. And I mean, I shied away from it. It's the thoughts initially of talking in my class. My God, they're supposed to sit down and stay quiet. In fact, it might be even moving around initially I thought it was awful. And you will hear teachers saying, I tried it and it was a disaster. I'm never going to touch that again. But you do have to stick with it, and but you need to come in prepared for it, that if you are going to use any props, that you have them already, or you have the question already done, or you're structured for it, that you're not going running looking for things in the middle of it all. It says it doesn't have to be done in all, it couldn't possibly be done in all classes, we just wouldn't get the curriculum covered if it was done in all classes. But it does encourage perseverance, and that's where the teacher comes in. Remember we said originally the teacher shouldn't, don't tell them too much, and it can be difficult for teachers. So you've got to go around with the group and not tell them, but ask them questions. Ask them leading questions, I suppose, in some ways, to try and push them in the right direction. Leave them off as I did with you, before I start going around then and asking some of you, we're nearly there, but you couldn't quite get it by asking you questions or doing things. Okay, you've probably popped that there, a few of you. Some ideas for teaching. Give the problems at different times in the class. Now that one there would be a full class activity. But you might give it to them as a lesson starter. I'll show you a few examples of these in a minute. The whole class we've just done are pot boilers. I'll explain what they mean in a minute. You could get, if you're lucky enough, if teachers are lucky enough to have their own classroom, they could design over time posters and have them up in the classroom, and at different times they'll put one up, leave it there for the week and see if students will come up with the solution to it. Or lucky dip, out of a box, people to pick a different question. But remember, especially at junior cycle, where most classes are mixed ability, we don't want students to be working on questions that are way too hard for them. But that's an ideal question, because most people can find the pattern. The weaker students may not come up with the reasons why, but they'll have a certain amount of success if they find 1, 4, 9. And even if they don't spot those as squares, or as the perfect squares, they could still slog through it to the bitter end, to all 100. And I know it takes a bit of time, but it'll give them good practice on being neat and tidy. And encourage participation then in problem solving contests. There's a few of them missing up there. Junior maths competition, particularly for the junior cycle students. So this is what we're talking about, a problem starter, where to build a fire station. And I always cursed my colleague who set up this slide, because I can't pronounce the 3 towns, somewhere on Honolulu, why he couldn't pick somewhere in Ireland or whatever. But anyway, we want to build a fire station that's equidistant from all 3 towns. Road building is no problem. Where would we build it? Now, if you haven't taught, this is a way of what we call a lessons or problem starter. The students can experiment with this. Just get them to draw 3 towns, 3 dots anywhere on their page or their whiteboards. And we want to put the fire station in here. Now they'll be there with their compass probably and measuring, trying to get the point in it. But it's giving them, I suppose, there must be some easier way of doing this. How on earth can we do it an easier way? So it's an introduction for you to teach them the circumcircle. And they eventually learn that if you make the triangle and get the perpendicular bisectors to the sides, they actually have the circumcenter where they'll build the fire station. So that would be a starter to whet their appetite, I suppose. Let them struggle with it, and then you have them at that stage then to want to know the short way of doing it. Pot boiler is something you could give a class and leave it for a couple of days. That's an interesting one. How many different ways are there to place 10 Smarties in 3 different bowls? Now we're not talking, the colours don't matter because there can be Smarties, there could be anything, there could be beans, there could be stones, anything at all. And you are allowed have an empty bowl. You don't have to have one on each one. That's an interesting one if you want to think about it over lunch. Okay, so we have 10 Smarties and we want to know how many different ways, and I'll come back to that in the afternoon. So again, back to our implications for the classroom. Problem solving, problems will come up in the exam, so it's a preparation for the exam, even though we're not necessarily always doing exam type questions. And I suppose a lot of maths classes up to this have been a bit more of the teacher doing all the work. I've often come out of classes saying, I'm the only one who worked in that class. I've been doing the work, I'm at the whiteboard, I'm going around to correct it. Students are there very passively absorbing, you hope, what you're telling them. So one of my colleagues calls it like a spectator sport, where the teacher is the performer and the students are the spectators. There's also this fear of getting it wrong as well, and you mentioned that, I think, in your feedback there, that you didn't feel that you're under pressure, you're the odd one out. If you're working in a group work, you have it. We're telling teachers that they can't really structure that I'm going to spend next week doing problem-solving questions. It's not a topic on its own. That it has to be done when you're teaching trigonometry, you have problem-solving questions attached to that. If you're teaching constructions, there's problem-solving questions. If you're doing numbers, that problem-solving should be, within every aspect, every strand they're doing, there should be problem-solving activities. But you need to pick your questions so that you are exposing the students to all the different strategies, so that when they get an unfamiliar question in the exam, that they have all of these strategies in their armoury to tackle the question. And that means that a different type of work has to take place in the classroom. So I think at this stage you've probably realised, if you hadn't realised already, that the maths class now is changing and changing drastically. And that is emphasised in that trial report I mentioned to you earlier on, and in the teaching and learning plans that we've developed with the project schools particularly. It's not just teacher-directed single approach. And we were saying that an achievable goal would be to introduce your first years and your fifth years to each of the problem-solving strategies over a period of time, but not to sort of take it as being, this is my week for problem solving, I'm going to get everything done in it. Now, there's an extra slide I put in because this report was published there after the project schools had an exam, their leaving certs, had a completely changed paper 2, and paper 1 was almost completely changed. And the State Exams Commission gave us feedback on it, and among many of the recommendations, this was the one they said, and I thought it fitted in nicely, that recommendation fitted in nicely with this set of slides that I have. So not to be put off or upset if a problem is not working out. These are recommendations to the students as well as the teachers. Some problems are intended to be challenging. When an examination task is non-routine, then you will be well rewarded for exploring the problem in a reasoned way and applying plausible lines of attack, even if you do not ultimately fully solve the equation. And I think that needs to be emphasised to our students, that they will be rewarded for any work that is leading them leading them in the direction of a solution, even if they don't get the solution. Okay, now this will only take a few minutes. We usually ask the students, the teachers at this stage in the workshop, to look at pages 5, 6 and 7. It's a reflection exercise. I won't be taking back any feedback on this. I don't know how relevant it is to you in your positions, but with the teachers, it's getting the teachers to look at the techniques they're using in their classroom, and whether those techniques, when you tick what you're using, a lot of people found that they were using techniques for teaching that were very teaching procedural work, and that they weren't maybe adopting, enough of them for problem-solving activities. So the first lot of questions are really for teachers to look at their own teaching practice, and the second lot of questions then, some people suggest that you give them maybe to students, and I'm talking about second level students now, and see how they perceive a maths class to be. So I mentioned George Polya earlier on, and there's a quote from him. So I think the key is setting them problems proportionate to their knowledge. I mentioned that earlier on, and I keep coming back to it again and again to differentiate the type of questions. We don't want to turn the students completely off problem solving. And while it may seem as a criticism to what teachers have been doing up to now, what we've been doing up to now really has been serving the needs of the students to get their exam in the particular exam that was there. So we've been doing that, I think, pretty well, and we just need to adapt our teaching methodologies to taking the problem solving. Now, problem solving questions, we have a bank of those on our website, and I'll be showing you the website in the afternoon session.